Welcome to Chronicles of the Curious, where we explore the fascinating and mysterious aspects of science and nature. In this video, we will discuss a new theory that challenges Einstein's general relativity, the most successful and widely accepted theory of gravity. This new theory proposes an alternative explanation for gravity that could have profound implications for our understanding of the universe. Let's dive into this intriguing and controversial topic and see what this new theory is all about. But first, a little bit about general relativity. If you find it boring, just jump a bit ahead and we delve into the new theory. General relativity is the theory of gravity that Einstein developed in 1915, after realizing that his previous theory of special relativity was incomplete and incompatible with Newton's law of gravity. General relativity is based on two main principles, the equivalence principle and the principle of covariance. The equivalence principle states that gravity is equivalent to acceleration, or that there is no way to distinguish between a gravitational field and an accelerated frame of reference. For example, if you were in an elevator that is accelerating upward, you will feel heavier, just as if you were standing on a planet with stronger gravity. Conversely, if you are in an elevator that is falling freely, you will feel weightless, just as if you were in outer space with no gravity. The principle of covariance states that the laws of physics should be the same in all frames of reference, or that there is no preferred or absolute frame of reference. For example, if you are in a train that is moving at a constant speed, you will not notice any difference in the way physics works inside the train, compared to someone who is standing still on the ground. These two principles imply that gravity is not a force that acts between masses, but rather a manifestation of the curvature of space-time, or the four-dimensional fabric of reality that combines space and time. Masses distort space-time around them, and this distortion affects the motion of other masses and light rays. For example, the Sun bends space-time around it, and this bending causes the planets to orbit around it in elliptical paths. Similarly, light rays from distant stars are deflected by the Sun's gravity when they pass near it, creating an effect called gravitational lensing. General relativity has been tested and confirmed by many experiments and observations over the past century, such as the precession of Mercury's orbit, the gravitational redshift of light, the gravitational time dilation of clocks, the gravitational waves from merging black holes, and the first direct image of a black hole's shadow. It is widely regarded as one of the most elegant and successful theories in physics. Despite its success and beauty, general relativity is not without problems and limitations. Some of these problems are theoretical, while others are observational. One theoretical problem is that general relativity is incompatible with quantum mechanics, the other pillar of modern physics that describes the behavior of matter and energy at the smallest scales. Quantum mechanics predicts that spacetime should be filled with quantum fluctuations or ripples at very short distances, creating a chaotic and fuzzy picture of reality. However, general relativity assumes that spacetime is smooth and continuous at all scales, creating a paradoxical and inconsistent picture of reality. This problem becomes apparent when we try to describe phenomena that involve both gravity and quantum effects, such as the origin of the universe or the interior of black holes. These phenomena require a theory of quantum gravity that can unify general relativity and quantum mechanics, but such a theory has not been found yet. Another theoretical problem is that general relativity does not explain why gravity is so much weaker than the other fundamental forces of nature, such as electromagnetism and nuclear forces. Gravity is about 10 to the power of 40 times weaker than electromagnetism, which means that a tiny magnet can overcome the gravitational pull of the entire Earth. This huge discrepancy is known as the hierarchy problem or the fine-tuning problem, and it suggests that there may be some hidden mechanism or principle that determines the strength of gravity relative to the other forces. Some observational problems are related to the existence and nature of dark matter and dark energy, two mysterious substances that make up most of the mass and energy of the universe, but have not been directly detected or identified. Dark matter is a type of invisible matter that does not interact with light or ordinary matter, but only with gravity. It is inferred from its gravitational effects on the rotation of galaxies and the formation of large-scale structures in the universe. Dark energy is a type of repulsive energy that causes the expansion of the universe to accelerate. It is inferred from its effect on the distance and brightness of supernovae and other cosmic objects. General relativity can accommodate dark matter and dark energy by adding extra terms or parameters to its equations, such as the cosmological constant or the scalar field. However, these terms are arbitrary and ad hoc, and do not explain the origin or nature of dark matter and dark energy. Moreover, they introduce new problems and puzzles, such as the cosmological constant problem or the coincidence problem. Therefore, general relativity is not a complete or satisfactory theory of gravity, and it may need to be modified or replaced by a more fundamental and comprehensive theory. The new theory that challenges general relativity is called gravity, which stands for a function of Ricci scalar curvature gravity. It is a type of modified gravity theory that tries to explain gravity without invoking dark matter or dark energy. Instead, it modifies the way gravity depends on the curvature of spacetime, by replacing the Ricci scalar curvature r with a more general function r in Einstein's field equations. The Ricci scalar curvature is a measure of how much spacetime curves or warps due to the presence of mass or energy. In general relativity, gravity is proportional to r, but in gravity can have a more complicated dependence on r, which can lead to different predictions and effects. One motivation for gravity is to explain the accelerated expansion of the universe without invoking dark energy. By choosing an appropriate function one can mimic the effect of dark energy by modifying gravity at large scales and distances. For example, one can choose a function that behaves like r at small values of r, corresponding to high densities and curvatures near stars and galaxies, but deviates from r at large values of r, corresponding to low densities and curvatures in empty space. This deviation can create an effective repulsive force that drives the acceleration of the universe. Another motivation for gravity is to explain the rotation curves of galaxies without invoking dark matter. By choosing another appropriate function one can modify gravity at small scales and distances, where it becomes stronger than in general relativity. This extra strength can account for the observed high speeds of stars and gas in the outer regions of galaxies, which are otherwise attributed to the presence of dark matter. Gravity is an example of a chameleon theory, which means that it changes its behavior according to the environment. In regions where the density and curvature are high, such as near stars and planets, gravity reduces to general relativity and passes the standard tests of gravity in the solar system. In regions where the density and curvature are low, such as in intergalactic space, gravity deviates from general relativity and produces new effects that can explain the cosmic acceleration and the galactic rotation curves. The new theory of gravity is tested and confirmed by comparing its predictions with observations and experiments at various scales and regimes. Some of these tests are similar to those used to test general relativity, such as measuring the gravitational redshift of light, the gravitational time dilation of clocks, the gravitational lensing of light rays, and the gravitational waves from merging black holes. Other tests are specific to gravity, such as measuring the growth of large-scale structures in the universe, the distribution of matter in galaxy clusters, and the motion of stars and gas in galaxies. One of the most recent and rigorous tests of gravity was conducted by an international team of researchers led by Baojiu Li from Durham University in the UK. They used supercomputer simulations to model the formation and evolution of galaxies in gravity, and compared them with observations from various telescopes and surveys. They found that gravity can produce realistic galaxies that resemble our own Milky Way, with spiral arms and central bulges. They also found that gravity can produce new effects that are not present in general relativity, such as enhancing the density and temperature of gas in galaxies, creating more massive black holes at their centers, and altering the shape and orientation of galaxies. The results of this study, published in December 2021 in the journal Physical Review X, show that gravity is a viable and consistent alternative to general relativity in explaining the formation and properties of galaxies. They also show that gravity can be distinguished from general relativity by future observations and measurements of galaxy properties. The new theory of gravity has important implications and challenges for our understanding of gravity and the universe. Some of these implications and challenges are: it offers a new perspective on gravity that does not rely on dark matter or dark energy, but rather modifies the geometry of spacetime in a more general way. It provides a new way to explore quantum gravity and quantum cosmology, by studying how gravity behaves at very high energies and curvatures near singularities or quantum fluctuations. It opens up new possibilities for discovering new physics beyond our current theoretical framework, by looking for deviations or anomalies in gravitational phenomena at various scales and regimes. It poses new puzzles and questions about the origin and nature of gravity, such as what determines the function how it relates to other modified gravity theories, and how it emerges from a more fundamental theory. I hope you enjoyed this video and learned something new about this new theory that challenges Einstein's general relativity. If you liked this video, please give it a thumbs up and subscribe to the channel for more videos on science and nature. Also, let me know in the comments what other topics you would like us to cover in the future. Thank you for watching and stay curious.